Good afternoon, ladies and gentlemen. We'll go ahead and get started. I have 3:15. This is, of course, Windows Vista Heap Management Enhancements. Adrian Marinescu is here with us and asking lots of questions. He's smart, so thank you.
Hi, thank you for listening. Hi, everyone. My name is Adrian Marinescu. I am development lead in kernel group. I joined Microsoft about 8 years ago, working on 2 kernel components, object management, local procedure call, and also user mode component, actually half user, half kernel, the heap management. So I came here with the white notebook, and people thought I'm going to have the presentation on a Mac. Well, in fact, it's not how it looks outside, it's how it looks inside. This is an x86 running Vista. And I'm going to, in some details about the Vista Heap Management and how we did about improvement in this area. So let's get started. I assume everyone here has at least some basics about the heap management, what the functions are, to malloc, free, and that kind of stuff. What is the role of the heap management? And I have just one question, actually. So who tried before to write heap exploits? Only one? Oh, 2. Okay. So maybe I don't see very well. And who was successfully running heap exploits after SP2? Well, it doesn't really make statistical sense because there are a few people, but anyway, it became harder after that, and we tried to make it even harder from now on. So I'm going to talk a little bit about the basis of the heap management. I'll cover the main structures that were involved before in exploits and are interesting for the security researchers. And I'll give some brief about evolution of the heap management. Then I'm going to dive into the Windows Vista heap, where I'll cover the security enhancement, I'll cover the performance and reliability enhancement, and also the new role of the Vista heap management, where we want to look at the Vista heap as a tool to improve the quality of other applications, including third party. At the end, we hope we have some time for some questions and answers, and also we have a bunch of demos showing some structures or some of the internal things in the heap management to see how it looks today. So security is an industry-wide concern. I don't have to argue about this. Anyone in this room understands this, and I'll just skip through this. I'm just making the point that it was a very important shift in Microsoft culture through trustworthy computing, where we are thinking from the security, we're thinking of security from a completely different, different perspective. And the heap management development is just one example of that, but you saw in previous talks, in many other components, we had a complete different approach. You have a much better thinking about how the security has to be thought to the process from end to end. And the anti-heap management has the improvements in Vista to address 2 things. So one, it's a strategic point in defense, and from the second perspective, it has to address the industry trend with respect to memory usage and multi-core scenarios, and introducing more 64-bit relevance to 64-bit computings. So back to the basics. The first significant change in the heap management was during the NT4 Service Pack 4, when the heap lookasides were introduced to address performance issues. Later on, during XP and Server 2003, and later on in 2003, some performance problems were addressed with the low fragmentation heap, which is a new front-end heap management introduced back then. And I'm going to discuss a little bit what is the architecture for the low fragmentation heap. And at the same time, in the security community, the heap exploits became more visible. And at that time in AXP, Service Pack 2, and Windows Server 2003, we had the first round of heap mitigations where we tried to take away the low-hanging fruits that people will use to run arbitrary code on a machine. And now in Windows Vista Heap, we had an even bigger step forward. First, to address the next exploits, the next round of exploits that were found, and also to increase the performance and address performance problems such as fragmentation, scalability on multiprocessor machines, and such. So here is the a broad overview where the heap code lies on, and you can see at the top is very thin layer of the heap wrapper functions that are exposed to applications in kernel 32 DLL. And here you can find functions such as heap alloc, heap free, heap realloc, so all these heap star functions, as well as global alloc, global free, local alloc, local free, and so on. That stuff is really boring from a security perspective. It's just a scene, right? So I'm going to dive in the anti-DLL part where the biggest part of the anti-heap management is implemented on. And I would like to focus on, there are three things you might need to consider here. We have a management of a big chunk of memory we get from the system, and this is the segment management. We may have an optional front-end heap, which examples that would be the low fragmentation heap or the leukocytes heap. And every single block that is over 500K, where the virtual threshold is, on 32-bit machines, are just direct call to virtual alloc. And the heap manager just keeps track of its allocations in order to release the memory when the heap is destroyed. So these are like the basic structures I'm going to refer in this talk, so I'll mention here. And I just wanted to focus on two things here. There is an array of 128 list entries. Let me see the mouse works. Yeah, so 127 of them are dedicated to hold free blocks of a particular size. You have like free lists for 8 blocks, 8 bytes blocks, list for 16 bytes blocks, and so on, up to 1K. And there is one special list entry there for every single block that is over 1K. Every number I mentioned before is only applies for the 32-bit platform. On 64-bit, all these numbers are doubled, so it depends on the granularity. And the non-dedicated free list started to be indexed. It has some hash to have a quick constant time lookup later, but it's not really interesting for this presentation. Another thing, the second thing I want you to notice here, there is an array of segments which manage the memory allocated from the system. And the array is limited to 64 entries. And the size of the segment usually grows in time in an exponential manner. So as we reach a limit and we try to expand the heap, the next segment is going to be to have the same size as the previous, as the entire heap usage before. So it's going to double every time, up to the moment where we reach a limit and we have to allocate as much as we can from the operating system. So inside the heap segment, there could be areas committed and uncommitted. So most of the time, the last segment in the array has a large uncommitted range, which is used like in time to allocate to commit more memory. Most of other segments will have uncommitted spaces all over the places, and even the last segment can also have uncommitted spaces over the places. So if we look at the committed space, here are the allocations that we give away to the applications, and every single allocation every single block has a header in the front that is used by the heap management to handle the request and to track the allocations, to track the free space, and so on. And those structures are actually very interesting for exploits because using that may trigger some code paths to be executed, and eventually end up in running some arbitrary code that that is intended by the exploit. So let's take a look a bit at the heap entry structure. So we have a size of the block, we have a preview size of the block in some granularity, and this is used by the heap manager to locate the adjacent blocks. So based on the size, we know where the next block is. Based on the previous size, we know where the previous block is. We also have some flags controlling whether the block is free or busy, whether this is virtual block, or whether this is right before an uncommitted range, so we prevent touching the pages that were not committed. You can see below, like from a debugger, how we used to be the heap entry in debugger a long time ago. Right after that, there's another structure present in the free blocks, and that was really very interesting for exploits. You probably are already familiar with those methods to use the free list removal. So the operation when we try to remove an entry from the free list to have an arbitrary write at the address with a value controlled by an exploit. And here is how the code used to look like a long time ago before the first heap mitigations. So we have here fetching the forward link pointer. And the next instruction, we fetch the backward link pointer. And the next one is actually writing at the backward link pointer value we fetch from the list, the value from the forward link pointer. So you can see this as a translation from an exploit perspective as how you can basically deter the heap algorithms to have an arbitrary write. And there are several variations to this. So one would be, have a buffer overrun. You go over the Rex header and you put there a free list entry, even if the block wasn't free before. And there are some other variations involving virtual lock blocks, and you have the list entry in the front of the entry. So regardless, there are like several ways the exploits took advantage of that. Another component of the heap manager is the look-aside list, and you can think about those as some sort of caches that the heap manager keeps on the front of the heap manager to have a very fast operation to alloc and free. All the blocks in the look-asides are not coalesced with the free blocks, and everything is disabled from that respect. The algorithms take no locks. Everything is done with the as I said, with non-blocking low-level primitives. And the header looks pretty much as a busy block. And interesting here is it just have just one pointer for the next block in this list. And the problem with the look-aside blocks, with the look-aside heaps, was that when we move toward like multi-processor scenarios and highly scalable servers, we may have contention, we may have cache collisions on the list entries. So like multiple threads running on multiple processor at the same time may try to do a push or pop operation for that S list, and that is going to invalidate the cache line for the processor. So this effect can be seen very easy in some of the benchmarks, and I'm going to show later what the problem is. And the loop